Thank you for the introduction. My talk is about... Is this working? Yes. My talk is about the link between information distances and resolution analysis with an example from radar signal processing. So I'm an engineer I hope, with a firm mathematical background. It will be information geometry from signal processing point of view. Yes. Sorry, I'm just ready. So here is the outline of my talk. I will first present you motivation for this work. It's a lack of performance metrics in compressive sensing radar. As you may know, compressive sensing is characterized by fewer measurements in data acquisition, what we call in an RF system front end, and in back end, the emphasis is on sparsity of the results. I will give you an overview of existing resolution matrix. Then I will link information geometry and in particular distances with resolution, propose stochastic resolution analysis, give some numerical illustrations, draw conclusion and indicate future work. I found it. So here is a block scheme. We engineers like to use block schemes. When I will just show you briefly a receiver of a compressive sensing radar where you have in data acquisition part what would be compressive data acquisition. You have an antenna array with 10 elements, and you have nowadays per each element you have a RF receiver channel. And then there are plenty of solutions how you can get those fewer measurements, fewer meaning less than an equisampled measurements. One standard solution is analog to information conversion given by compressive sensing theory, but there are also some more elegant solutions like getting fewer measurements before reception by means of sparse sensing. So here is just for your illustration and maybe a refreshment of compressive sensing paradigm. And in the back end, what we call is an emphasis on sparsity. So we call it sparse signal processing. So here, the discrete measurements Y are acquired, and the output, the result of the whole process out to receiver is radar profile X in a scene, what the radar is looking at. Then, so far we know that there are promising benefits from compressive sensing, and in particular from sparse signal processing, even given equisampled measurements, and those are high resolution. Multi-target analysis would be quite elegant, but somehow there is a lack of performance matrix in detection, resolution, and accuracy. The model we are using is a linear model where measurements are described by a sensing model matrix A, given on discrete grid of unknown parameters theta, and profile X, which contains amplitude of at that discrete grid. And then we have, of course, at least disturbances being receiver noise, which can be fairly modeled by complex Gaussian noise with zero mean and equal variances. And the usual solution from SSP, sparse signal processing, is with norm 1, where norm 1 promotes sparsity, and of course in this minimization the squared Euclidean norm minimizes the errors. So here's again the question. SSP provides high resolution. You can find all over in the literature, but it's not quantified how high. So first, before I'm going to talk about using information distances, I will give a short overview of existing resolution matrix. And then with a simple example of complex Gaussian measurements with mean M, given the unknown parameter theta, one single parameter, and the model where we have only single parameter theta, we would call it single source in wireless communication of single target in radar, and the mu being observation vector. You may see it from each antenna element comes one observation. So the primer resolution meter of primer resolution description comes from a Rayleigh limit, we call it, of maybe distances is a not proper word in this community. And that depends only on a sensor design. So in this case, it will depend on array sensing bandwidth, which I called here mu b. Then if we, besides sensor, what sensor can do in resolution, if we involve also the sources or the targets of the scene which a radar looks at, we come to stochastic description because we involve signal-to-noise ratio of the targets and their separation. And the first approach in a stochastic description would be estimation approach, where for decades people also like to express the resolution capability with the best accuracy of estimated parameter theta, given the signal-to-noise ratio and given again sensor design. And then the next step in stochastic description would be detection approach, that we describe a resolution and as probability of resolving targets at given signal-to-noise ratio and separation, again with given sensor design. This would be a quite complete description of resolution, what we would also like to have in the practice when building actual radar systems. So, and what is new in my work, I'm introducing information distances for a complete resolution description. Now I will try to link information geometry and in particular distances with resolution. So information geometry is about distances between probability density functions. And in resolution analysis we have two probability densities, one with the theta and the other with the theta slightly different. And or in this example, from radar signal processing, we have two complex Gaussian distributions with the mean given a theta and the other mean given a slightly different theta. I started first to look at those differences between those distributions related directly to the unknown parameter, and I used all the machinery that all of you are familiar with, and I ended up with a very simple expression in that simple case with one unknown parameter from an angle, you may call it angle from antenna array, where the distance is here. Distance is a linear function of the separation in angle in this simple model. So that was, and then I proceed with the other distance related to the model function. And so that this is a distance got from that work. And this is a bit more complete and more realistic. And I will show you that in this plot. So the linear, the simple distance related directly to the unknown parameter, in this case angle, is a linear function of separation being on x-axis. And the other distance is as a kind of reaching it's a maximum at the, this is given, the separation is given in an Rayleigh limit. So at the Rayleigh limit, giving the maximum and then oscillating a bit, and then after very large separation, it's a constant. And what is also interesting, this distance, if it is a Mahalanobis distance, is also in Gaussian case directly related to Kullback-Leibler divergence, which you can see here with the dotted line, and with the Bhattacharya distancing here with the dashed dotted line. So this is a connection between resolution or probability density functions from which we are dealing with in a resolution analysis and information distances. And now I also have to express the resolution with probability of detection, probability of resolution. So I'm following a resolution test of binary hypothesis test from work of Rao, from initial work on information geometry, which under zero hypothesis it would be there is no difference in unknown parameters, and the other hypothesis would be there is difference in an unknown parameters. And in our case, it would be, in that example from radar signal processing, it would be zero hypothesis, would be there are two targets with precisely the same model functions and a noise. And in the other hypothesis, it would be one target would have a slightly different parameter. And I will test this binary hypothesis as we are used to in signal processing with the likelihood ratio test. And I will try to see a link between that likelihood ratio test and information distances. Whether the information distance I analyzed previously would appear in a likelihood ratio. So I developed a log likelihood ratio, and indeed the log likelihood ratio is related to the information distance, related to the model function. So this is a novel. What I done, I expressed likelihood ratio distribution and link it to the information distance. What I present here, and I will also present to IEEE CompSUP, but more related to compressive sensing and then sparse signal processing framework. And so I can express in the end probability of resolution at a certain SNR and with all the crucial ingredients we need in resolution analysis, because I know the distribution of log likelihood ratio. So I'm giving you a numerical illustration. So I'm going back to my motivation problem. I will assess probability of resolution from sparse signal processing numerically. I say it's resolved if in the cells where the source of the targets would be if it's solved by SSP, if it's not zero. And then I will also extend the model with two parameters, but both in an exponential function. First would be in spatial domain, U as an angle we already had, and the second in temporal domain would be Doppler. So first plot is I let those two targets differ only in angle by one Rayleigh cell, and then be same in a Doppler. So you see here two probability of resolution. Blue is a numerical assessment from SSP. The green one, full line, solid line, would be bound with information distances with respect to the model function, and the other bound would be directly computed with respect to the unknown. If I let two sources differ both in an angle and in Doppler, the initial bound would go quite unrealistically, quite optimistically very low, and the other two results would remain more or less the same. What is in accordance with if you remember, with the information distances you just saw in the plot. They reach a certain maximum, and then especially after a Rayleigh limit, they remain more or less the same. So I may conclude from this that SSP, first of all, that's my initial question, SSP resolution is quite far from the bounds, even from the tighter bounds, about 4 dB. And that as I already said, the initial bound is optimistic at larger separation. It grows because the information distance grows linearly with the separation, while tighter bounds with respect to the model function remain realistic, as well as the information distances. So I will draw a conclusion and indicate the future work. So I presented you resolution bounds for multiply parameters in complex Gaussian measurements from sensor design, in this case example of 2D array, spatial temporal array. I derived the probability of resolution at given separation and SNR of targets, and assess it via a likelihood ratio test by exploiting the information distances in the distribution of the log likelihood ratio. Sorry. wrong. And what I may conclude, and what is important for us in an actual radar system, this analysis shows completeness and suitability for essential performance metrics, here given in radar example, but not limited to the radar. And what is also very interesting and exciting, shows also close ties as the separations getting smaller, shows close ties between facets of performance, detection, accuracy, and resolution. And what is also, what we can conclude that SSP resolution is quite far from the resolution bounds. And in the end, I would like what I've showed is given with the Nyquist sampled measurements. I would like to do this analysis with fewer measurements, what is typical for compressive sensing. And moreover, in order to do that, I need the reference, and the best reference is in continuous domain, in analog domain, to compute before any sampling, to compute the dose bounds. And as one reviewer from this conference kindly recommended, I will also try to incorporate sparsity into the resolution analysis via the geometry of the Laplacian manifold. So that was my talk. Thank you for your attention.